Hey, I'm Bill Zehrt. I work for the Department of Defense Explosive Safety Board in Alexandria, Virginia. I've actually been there, amazingly enough, 16 years now. I was at the Corps of Engineers in Huntsville before that, starting in 1988, so I'm old. So I have worked primarily in explosive safety, obviously, for the last 35 years, but there is overlap and there's confusion also between explosive safety and anti-terrorism and other user groups. So my presentation is focused on trying to explain the differences and hopefully prevent people from using the wrong guidance for the wrong protection. So here's my outline. I'm going to start off with the basics. So what are the design basis threats used by different user communities? Because that's important. It actually will go a long way to explaining why we have different design requirements. I'm then going to go through the performance objectives that we apply to meet the design basis threats. Give an overview of the different blast analysis and design procedures that are used by each community. And then the main focus is my venting session on where things go wrong and things to watch out for, I guess you could say. Okay, so the design basis threat. I think a lot of this is just obvious. Anti-terrorism, I actually didn't know how the process was working recently. They've updated their guidance. But essentially, within DoD at least, there is an effort by the planners to look at security and anti-terrorism together. And what the cost is above a baseline cost for, if you didn't do anything for anti-terrorism or security. And it's a trade-off study between the two. And, so it can vary from project to project, how critical is the asset you're protecting, how many people are exposed, what have you. But it's not like a rigorous, you do this, you do that. It's more of a nuanced approach, I guess you could say. Typically with anti-terrorism, it's an external threat. There's very limited guidance for like a mailroom, but generally it's just like, don't put the mailroom in the middle of the building, put it on the edge of the building, things like that. Common sense stuff. Typically external. You don't know, obviously, what a terrorist is going to bring to the event, but you can get an idea of what they could bring. So, and along this line, with all our communities, we like to use distance to mitigate the hazards. So if you're further away, you're not going to have as high overpressures, the fragments won't be as bad, you might be able to avoid thermal hazards. So we often use bollards around like courthouses and things to keep the distance away. So if someone has a vehicle, they can't get closer than X distance from the building. Conventional weapon attack. This is, I would say, the most advanced of the three groups. It's also the FOUO manual because it gets into weapon effects. And they're looking at typically an external, although it could be internal also. And it's conventional weapons attacking a target and trying to keep the target operational. Explosive safety, so there's good and bad. I mean, we have lots of exposures, obviously, because you've got ammunition from initial testing, development, production, storage, demilitarization, the whole gamut of things with explosives. The nice thing, though, is we get to decide where the explosives are. We get to decide what the bay looks like. We get to decide how we vent it. We have control over many things that the other communities don't. So in that sense, we're able to have more refined requirements for protection, I guess you could say. So performance objectives, this is key. Anti-terrorism, and this is from USC 40101, but it's a general for, I think, throughout the industry. The main focus is to prevent a catastrophe, prevent lots of deaths or injuries, prevent building collapses. You can't protect from everything, but you want to protect from horrible results. So That's the focus. Hardened structures, like I said, you want to continue to perform your mission. So whatever you're doing in that building, you don't want someone to be able to attack you and take out that capability. Explosive safety, I was thinking it's like a God and country. We try to protect as best we can from whatever we can, which is of course true. But at the end of the day, it's, a couple things. You can't do absolute safety because it would be so inefficient and expensive. It's not possible. Also, in addition to, there's a criteria to protect people when the risks are high from an event. But a lot of what we have is capability. We don't want a blast in one magazine, say a storage magazine, to take out 50 magazines. We don't want a blast in one production bay to take out the whole building, So there's criteria that are very much drawn on that, on retaining capability. Okay, so here are the different standards that are used. I'm sure you all are familiar with these. I would imagine most of you are. There's UFC 401001, and that is, in the first presentation there were response limits from PDC, from Protective Design Center. Protective Design Center is, I would say, the key player on 40101. So those are anti-terrorism protection. As was mentioned, as Ganesh mentioned, there's been work done on glazing. So the focus for anti-terrorism is not necessarily that the glass won't break, but if it breaks, it's not going to break in a way that causes terrible injuries, right? You don't get sharp shards. You get a less hazardous debris. And there's a separate UFC for progressive collapse as well, which I think there was a GSA. There's different groups that are in anti-terrorism have that. The ASCE blast standard, it's interesting because I was in that group from the beginning, and initially it was thought that it would be kind of like what would take over for 40101, but they kind of, well, they're very similar, but they're not exactly the same. It's an ASCE document. So it's ACA membership determine requirements, and they don't always agree with PDC. But they have the same they have the same protection levels and response limits. So they have the same fundamental basis. It's just, what criteria do they apply then, like as far as response limits for elements? They can vary. I wanted to point out, it's the main reason I'm on this committee, the scope says it's not for explosive safety. So there's the quote that goes a great deal about why it's not for explosive safety, because we have different protection requirements. One thing with AT, which makes sense, is there's a lot more focus on conventional materials. It's an external blast, so you just have a shock load. You try to get some distance away. So you try to use conventional materials when you can. Sometimes you can do some minor upgrades to the materials, and they can resist the blast load. So there's looking at things like that that you can do. But it tends to be more focused on using normal construction versus explosive safety or hardened structures, where we are designing for a significant, usually, event, often internal. It's not going to look like a regular structure. It's going to be very robust and heavily reinforced, so it's different. And with anti-terrorism, you usually don't consider fragmentation or thermal. It makes sense. If it's external, for the thermal, it's usually not the predominant hazard. The overpressure would be the predominant hazard. And fragmentation, it's just almost impossible to know what it could be. If a car bomb goes off, what are your fragmentation hazards? I mean, and you're still tied to this prevent mass casualties, typically objective, so, also would make it almost impossible to do windows and things. Okay. So I'm going to go, this is my explosive safety in my area, so I'll go in a little more detail on the UFC. It's been around a long time. It was initially published in 1969. It's always been open distribution. It's used a lot, and we're grateful to be able to help other communities for sure. But you got to remember, when it was 1969, the understanding, even of of earthquake loads was fairly limited. And so it's written so that somebody can hopefully have enough understanding to cookbook their way through and get a safe answer and a reasonable answer. So it gives very detailed examples and step by step, and it gives a lot of explanation. It's based on single degree of freedom and multi-degree of freedom models, so those are accessible to most engineers. They can pick that up. And since it's open distribution, I think if the hardened structure were open distribution, there'd probably be a lot more reference to it. But since this manual is open distribution, it's referenced quite a bit in Chapter 9 for procedures. Okay. So this illustrates some of the differences in explosive safety. So we have historically had criteria when an operation is a higher risk type operation, like it's a research or whatever, and there's a more chance of a detonation, to try to give greater protection. In '69, when the manual was first released, some of these criteria, the overpressure was there, but the others were more vague. They weren't defined numbers. In the '82 standard, we introduced all three, as the protection requirements for personnel. So when we're designing something for personnel protection, this is what we have to ensure, that someone isn't exposed to like a higher pressure than 2.3 psi incident, a hazardous fragment, which is like, that basically corresponds to a fatality, not a fatality, you're taken out of action. It's like one maybe 20% chance of fatality. I don't know. It depends on the modeling, but you're seriously injured, put it that way. And the thermal flux is for second degree burns. Then we have the other categories, and the last three are all tied to saving assets, not losing capabilities. So you can either, protection category 2 is more rigorous, and then you don't want your equipment damaged. So it's more rigorous than 3 and 4. And 3 and 4, what you're looking at is you've got a building with, like I said, say 10 bays with 100 pounds in each bay. If you do protection category 3, prevent communication, the one bay can go off, but it's not supposed to propagate to the next one. So basically the wall can be an incipient failure. It can be not much left, but you don't get a propagation. Protection category 4 is just, you could have a propagation, but there will be enough of a time delay that the blast waves won't coalesce. So there are situations where that would be, that distinction might be made, but in all honesty, we apply the same design requirements to both. So we have the categories, but we really do 3 regardless. Okay. Now the meat of the talk. What can go wrong? Okay. UFC 3-4002 is it's a DoD document. It's for DoD facilities, on DoD installations, and, it has broad use. The methodology works for whatever the blast is, but the testing and what it's based on are what DoD needs and really what the services need. We have many explosive operating, storage, manufacturing, blah, blah, inspection bays. We started building these with concrete walls during World War II, and with the idea of preventing a propagation or a prompt propagation, but nobody knew what they were good for. I mean, it was the ability to test, and it was World War II. So you would get like 50,000 pounds for one service would say, 65,000, somebody else would say 30,000 pounds, what have you. After World War II, they did some testing, and it was kind of like a Stonehenge test with walls around a detonation, and they came up with 5,000 pounds was safe to prevent a propagation. So that was in our, that was our requirement. But then, unfortunately, during that time period, more than now, there are accidents and things happen that you don't expect. And so they start to think, maybe that's not quite right, maybe we missed something. Anyway, in 1959, they set up a working group to actually do tests in cubicles. And I'll just move forward to that one. Show you what it looks like. So this is what a cubicle would look like. This is one we did in a study. It's not, it's just it's a general idea. It's not any specific design. But they did tests in the cubicles, and they started at 5,000 pounds and got a propagation. Then they did like 2,500 pounds and they got a propagation. And they did like 1,000 pounds and got a propagation. And they did like 500 pounds and got a propagation. Anyway, they recognized, and it seems weird to us now because this just is intuitive to us, but they didn't know there were gas pressures. They didn't know there were shockwave reflections. They had no grasp that an internal would be different from an external event. Anyway, they did the testing. It went through several iterations looking at different service typical structures. And the data from that was put into UFC, the initial UFC 34002. It was a tri-service manual then. Let's see. I might be getting a little ahead on my slides, but I'll go ahead and mention this. One thing you can notice in this picture is the cubicle, one, it was tested in the open initially, so it vents better. We did subsequent tests with frangible, surfaces for the roof and exterior wall, but initial ones were open. But our tests have always, what we base things on are tests without openings in walls. So, what unfortunately has transpired somewhat is the UFC says you don't have to worry about thermal hazards. You don't have to worry about thermal hazards because when you use these, you inset the roof and the exterior wall. Concrete's very effective at fire protection. If it's 1-1 and it detonates, the overpressure and fragmentation control your damage and what you have to protect. And so you can generally ignore thermal. But that doesn't mean you can always ignore thermal. You start putting a door or a opening in a wall, you may have a thermal problem, particularly if you start using more robust construction for the roof and exterior wall. Once that stops venting, and then you have openings, well, the fire's going to go where there's oxygen, and it's go whatever pathway it finds. So anyway, that is lost sometimes. Okay, I probably have gone through this. I'll do this as a roll-up. So the UFC focused on, it has a lot of reinforced concrete design guidance because we have fragmentation hazards. Okay, I'll try to speed through. We have a lot of fragmentation hazards. It focuses on internal blast. It focuses on continuously supported walls and slabs because we have that a lot, although it also has like flat slabs and columns, more limited guidance. And it's strangely, like if you go in structural steel, there's a big section on corrugated metal deck wall roof systems, which just seems so weird, but that's because in the 70s they had a test program looking at vent surfaces and trying to develop vent surfaces that would be frangible outward, hardened inward. So basically you have these panels and you put the supports on the inside face, you just connect them with washers or lightweight connections so they pop off easily. When the blast wave comes around, they bear against the supports. The blast load passes, they can pop off then and rebound, but nobody cares because the load's gone. So anyway, okay, real quick, and this is getting a little outside of the scope of the ACI, but I wanted to mention it. We in DoD have been moving towards insensitive munitions, which also leads us towards moving toward weapons that have mass fire as their primary hazard instead of fragmentation and overpressure. And so if you have a mass fire item, it's different. The overpressure rises gradually. There's not severe fragmentation. There may be very little fragmentation. And the temperatures can be much higher than a conventional fire. And so you can see that if you have a cubicle and you confine it, that's really bad because you don't get pressure to pop off panels, you don't get pressure to pop off doors, you have this very robust fire and it's going to go where it goes. And we have no way to really analyze that at this time except very roughly. Okay, the rest of these are pretty easy. Don't shop for blast design requirements. Don't say I'm doing explosive safety, but I'm going to use this HEFP protection level, and I don't have to worry about fragments because I'm using ATFP. You have to satisfy the protection that's required, not satisfy what requirements are in a book. You make sure you're doing what you're supposed to do. Okay, this has been probably the biggest problem we've had. I mentioned earlier that early on, the planners determine what they need to do for security and anti-terrorism. And we've had some major designs where that step happens before the designer really is even on board. They decide to harden everything. They blast resistant exterior walls, blast doors, almost no openings in the roof, and then we have 1-3 in it. And they have clear openings inside the cubicle for penetrations because they want to be able to pass things through, so they just have an open slot and people on the other side. And you're just like, no, you can't, and it's problematic for us because we don't have, we have the experience to know you shouldn't do that. That's not what things are based on, but we can't point to a requirement in the TM that says you can't do that, but we can't validate it, obviously. That's a problem. Okay. Wait, I probably went it. Let's see, can I go back? Let's see. Okay, let me do this. Okay, there we go. I'm sorry. This next one's a dumb one. People get codes that don't know how to do blast design and they just make it work, essentially. So we had one design by a non-civil engineer, non-structural, where they used the fragmentation plate as rebar area and got really high resistances in the walls, so everything worked. It was an existing facility, but of course that makes no sense. That plate just has a few anchors tying it. It's not going to act compositely. It's wrong, but you can get that. People play with the damping ratio until they get it to work. So damping ratio is a elastic response, but if you use like a damping ratio of 30, you can meet that 12-degree support rotation. So makes no sense, but people do that. That's why we check designs, I think, because people do that. Last thing of these issues, don't over-design, because the way the design works, you design in flexure, you have a response limit like 2 degrees support rotation or maybe 12 degrees. If you design it for like 0.2 degrees and have a much higher resistance, everything else has to use that resistance in design. So you're designing because you don't want a failure to occur in a non-ductile mode. So your diagonal bars have to be for that resistance, your stirrups have to be for that resistance. If you need tension bars, they have to be for that resistance. It's a nightmare, and it's an avoidable nightmare. Let's see. Sorry. That's my big go-to slide. This is just to show you what a wall looks like. So the left one is like if you have a close-in load, we have requirements for the stirrups that they have 180-degree hooks, which contractors hate. But you can see it gets pretty congested. That's why you have the wall extensions, so you don't have all the hooks. We often don't have those extensions, and you have to hook bars in. But you can see it gets congested pretty quickly. On the right is if you've got a far range loading and a lower support rotation limit, and you can use 90, 135-degree hooks, which are so much easier to place. But it also shows where the tension bars would be if you need tension bars in a cubicle. And that would be like if you've got a wall on each side, the side walls, and there's a blast, well, the back walls can be put in tension. So you need the mid-depth tension bars then added. Yeah, kind of ruined this surprise. This is why you avoid over-design. This is one of our major projects from the 90s where there was, so this was unfortunate, the wall, they designed the thickness early on, and then they had all these openings that they didn't expect, so they have you can't see that, but around the openings is just a massive congested rebar because you have to take the load out that's on the penetration. And then we have like guidance for how to place concrete, but they thought they could do it. and they had a truck not make it on time. I mean, it was ridiculous. It was just one thing after another. But this is what it looked like when the forms came down. So yeah, self-consolidated concrete is a good thing too, I'll add. But yeah, don't over-design. So finally, make sure you know all the uses of protective construction on a design, and also know what they're for. Like, is this an anti-terrorism? Is this explosive safety? So you know what you have to meet for protection. Let's see. Use design charrettes to figure out, we strongly recommend that, what's a viable approach. We have some designs, so you can either do a containment structure where the weight's relatively low and you contain the blast effects and vent it away from the building. But if the charge weight gets too high, you have to use a shelter approach where you let that bay, you know, could be destroyed, but you're sheltering people and you're hardening where their shelter is. If you use a containment design and it's like 1,200 pounds, it's just never going to work, and it's going to be a mess. It's, you know, so just really think through what you're doing early, because once you get into it, it's very hard often to change. And when you can't change it often, either somebody has to accept the risk, or there's a huge brouhaha and contractual nightmare, and you know, you don't want to go there. The last thing, and this is really geared to the 1-3, we really need research and testing to evaluate 1-3 hazards. That's the mass fire stuff. What makes this really challenging is, you know, for 1-1, you know you have an explosive and you can get a TNT equivalency and then you do your design. For 1-3, the hazards very much depend on the configuration. You can have a block of 1-3 you can have it sitting on your desk. It's not hazardous. But if it's flaked and it goes off, it's really tied to the surface area, what thermal hazard you get, and it can be devastatingly bad. So it's much more complex. Anyway, I appreciate it.